Hello, hi everyone. This video is on IGCSE Physics 0625 for Year 11. We're going to discuss on topic 4, electricity and magnetism. We're going to focus on electromagnetic induction, Fleming's left-hand rule, or we call it as generator effect. At the end of this chapter, students should be able to show understanding that a conductor moving across a magnetic field or a changing magnetic field linking with a conductor can induce an EMF in the conductor. Conductor here means wire. Second one, students should be able to state and use the relative directions of force, field and induced current, basically by using right-hand rule. A current produces a magnetic field. However, the reverse is also possible. A magnetic field can be used to produce a current. In this diagram, when a wire is moved across a magnetic field, there will be a small EMF or voltage generated in the wire, this wire. The effect is called electromagnetic induction. Scientifically speaking, EMF is induced in the wire. If the wire forms part of a complete circuit, the EMF makes a current to flow around the circuit. This can be detected by a meter called Galvanometer. Sometimes they even use sensitive voltmeter or sensitive ammeter to replace this galvanometer. So basically, we have a magnet here and the field in this magnet from north to south. We take one wire, we move up or down so that the wire cut the magnetic field, and from there, current or EMF can be induced in the wire, and the direction we can determine by using right-hand rule. So the difference between galvanometer and ammeter, the one that we use to detect the direction of the induced current or EMF. Basically, galvanometer show both the direction and the magnitude of the current, but the ammeter only shows the magnitude of the current. Magnitude means that the value. Here are galvanometer, ammeter and voltmeter in real life. They look like the same, but actually they are different. They measure different things. For galvanometer, it is very sensitive to a small change of current. Ammeter is used to measure current, but then it is not very sensitive as galvanometer, and it just shows the value only. Voltmeter we use to measure voltage or potential difference. If a straight wire in a complete circuit is moving at right angle to a magnetic field, the direction of the induced current can be found by using Fleming right-hand rule. So, by using this rule, we can determine the direction of the induced current. Okay, let us see this figure. Okay, we have wire, we move it upwards. So, the motion or the direction of the force, okay, F here, for thumb rule is upwards, and the first finger is the direction of magnetic field, which is always from north to south. So our finger always show to south. And the current that is produced in this wire in this direction. So the current goes from positive to negative. Okay, so just remember FBI for these three fingers. When a current causes motion, the left hand rule will be applied. When we have motion that cause current or voltage to be induced, then the right hand rule is applied. Let us look at sample question 1. The wire XY shown in the diagram is connected to a sensitive voltmeter with a center 0. Okay, sometimes they will connect here, like we discussed earlier. They will connect either sensitive voltmeter, galvanometer or ammeter. XY is then moved quickly once through the magnetic field. So move quickly once. What is observed on the voltmeter? Okay, let us look one by one, A, B, C, D. The needle moves briefly in one direction and then returns to the center. B, the needle moves quickly in one direction and stays deflect. C, the needle vibrates rapidly from side to side whilst X is moving. D, the needle stays still. Okay, so here the movement only like once and it is quickly. So the answer will be A. Okay, why? Because this wire, this conductor, only cut the magnetic field here once. Okay, and since it moved quickly, so just the deflection in the voltmeter just briefly in one direction. One direction means that we move only one direction. And then it returns to the center. Why it returns to the center? Because there is no more cutting through the magnetic field. Instead, the wire is not cutting the magnetic field anymore because we move from here to here and then we stop. Okay, let us look at B. Needle move quickly in one direction and stays deflect, which is wrong. Okay, because whenever the voltmeter here we have the reading there, means that whenever the voltmeter have the reading, means the conductor is cutting the magnetic field. C. The needles vibrate rapidly from side to side while XY is moving. Side to side. Okay, since we have like one direction here, so cannot be side to side. If side to side means that we move here and to and fro. Okay, the needle stays still, cannot be, because the conductor is not always cutting the magnetic field. Okay, we go to sample question number 2. The diagram shows a copper wire XY connected to a resistor. The wire is then moved in the magnetic field between the poles of a magnet. There is an induced current in the wire from X to Y, so the current is this direction. This is the direction of current. In which label direction is the wire moving? So since here we have already the direction of the current, induced current here, so we use right hand rule. Okay, the current is from X to Y, and then the magnetic field is the opposite direction. So the magnetic field is from north to south. Okay, and then the force here should be downwards since our magnetic field. Okay, this one is, the first finger is for magnetic field direction. Thumb here is for force and second finger is for current. So since the field is in opposite direction, so the force is actually in opposite direction. So the answer is D, downwards. I hope that from what we discussed just now, you know how to use right hand rule to determine the direction of induced current. And thank you everyone.